Okay, excellent. So yeah, as Prudencio mentioned, I got my PhD in material science at the University of Pennsylvania, where I focused mostly on physics and materials theory. Later on in grad school, I was an affiliate scientist at Berkeley Lab with the Materials Project, which is where I really got interested in more sort of high throughput virtual screening and discovery of materials and molecules. And artificial intelligence, kind of as I became a core contributor with the Deep Chem project. And more recently, I've been a postdoc at MIT, working with the Lincoln Lab Supercomputing Center and Professors Connor Coley and Rafael Gomez Bombarelli. And here I focused more on these issues related to scalable deep learning and AI-directed design. So I'm going to give kind of a broad overview of the sort of problems and things that I've been interested in lately. And sort of the framing that I like to think about is all of the amazing progress that's going on in these sort of fields of high performance computing, deep learning, and the sciences, and particularly chemistry and material science. There's a lot of really exciting stuff happening in those fields, but they're largely disconnected. And I like to kind of occupy this middle space here at the intersection of all three of these fields. In particular, there are a lot of really exciting new AI and ML methods coming out all the time. If you try to keep track of them, it can be quite overwhelming. But if you're in more of an applied domain, like say chemistry or drug discovery, it can be really difficult to figure out what methods to use and apply to your problem, and especially apply them at scale if you're doing, kind of interested in problems sort of beyond small scale benchmarks. And so a broad question that I'm interested in is, where can we take lessons from fields where deep learning has traditionally been extremely successful, like natural language processing and computer vision? And where can we apply those lessons to chemistry and material science? And where do we need to change things? Or maybe not apply those things directly. So I'm going to be talking again in sort of an overview about scaling deep learning for atomistic systems with respect to a couple of different key resources, including compute, energy consumption, and model size and data set sizes. And to do that, I'll be talking about applications to molecular property prediction and regression, more specifically to machine learning interatomic potentials, and trying to accelerate physics-based simulation and improve it with deep learning. And I'll talk a little bit about recent work on chemical generative modeling as well. So a lot of topics, but really with the focus on investigating how these different applications scale with respect to resources and how we can do that intelligently. I'll be focusing on geometric deep learning, which of course as an architecture encodes the kind of geometric priors we care about in chemistry. It's also a nice term because it sort of encapsulates almost anything that you might want to do. So it's quite flexible. I'll be talking about transformers and graph neural networks in particular. And again, the sort of goal and approach here is to identify and figure out how to scale architectures that match the problem descriptions that we care about in chemistry, and try to sort of replicate and build on what folks have done in fields like NLP and computer vision. And so I'm going to be looking at how chemical transformers and graph neural networks scale for these problems. A framework for trying to start to understand this is called neural scaling. And neural scaling is an idea that sort of a bunch of large organizations, including OpenAI, DeepMind, and Google, have all contributed to recently. The Stanford Computer Science Department as well has sort of put out a big sort of paper very much related to this. And the sort of overall finding is that these large networks, you could call them foundation models, If you don't like that terminology, you could just say, a large network trained on general tasks in pre-training that you hope to use for other tasks, maybe a bit more wordy, but descriptive. And so the key finding is that these sorts of models, in some limit, obey simple power law relationships as you give them more compute, more data, or make the models larger. And so that's shown on one of these sort of classic neural scaling papers for natural language. You can see on a log-log plot these just like very simple power law relationships with respect to these different parameters. Why should we study neural scaling? Why is this something that folks are interested in, that I'm interested in particular? One finding is that when we take these large models, you sort of would classically worry about overfitting, especially to the sort of small data sets that we're sometimes working with in chemistry and material science. But it turns out that if you have a large model and you employ regularization techniques like early stopping in kind of a clever way, these models can actually be more sample and compute efficient than a sort of one-off model, maybe a smaller network that you train for a specific task that consumes fewer resources, but may actually be less efficient than this other approach. Neural scaling, some sort of more recent results show that neural scaling provides maybe a sort of best case scenario for model performance. It's probably not the case that you can simply look at those plots I showed and sort of extrapolate out to, okay, if I just had an order of magnitude more data, this is exactly how well my model would perform. That might not quite be the case. You might run into bottlenecks, but it gives you at least a sense, a very strong sense for the best case scenario of scaling. And when you're evaluating a new model, if you just look at this sort of single point comparison of a small model on small data sets using small compute, that might tell you very little about how that's going to do as you scale to new problems and bigger problems. And then maybe theoretically, the interesting thing is to ask, as we scale up models, of course, certainly from a physics perspective, we're always looking for this kind of emergent behavior. Do new surprising things happen that we didn't anticipate? Can we understand what drives scaling exponents? And maybe take this so-called Sutton's bitter lesson, which is kind of about the fact that scaling up with respect to compute tends to beat over long enough timescales, tends to sort of beat clever architecture decisions. Maybe that's not the case here in chemistry, where we have a lot of physical priors that are very mathematically sound to build in. When we're thinking about how to scale atomistic deep learning, what are the sort of knobs that we can play with? Here I'm showing, as we increase resources, and I'll give some examples for what that might be, what sort of performance might we expect if we take like a traditional model, let's say like a random forest or something. This is going to saturate out at some point. The thing that in some cases makes deep learning interesting is that this performance can continue to increase as you leverage increasing resources. So we might say collect more data or better data and then sort of extend this scaling along this curve. We could innovate on the model architecture and actually change the slope of this scaling and get better performance for a given amount of resources. And then we could do all types of optimization with respect to our software backend, our hardware, and again, kind of get better performance for given resources. So I think these are kind of three key data, model, and computer, sort of three key resources that deep learning uses to scale effectively. We want to see, how do we do that? How can we enable that for atomistic deep learning? And in particular, here at MIT, we have a program on AI-directed experimental design. And this is sort of largely where I work. And the vision is really to span lots of different discovery problems, from biotech to materials design and climate technologies, and have some kind of robust general infrastructure that helps you along these problems and drives impact across the things we care about, like representing complex molecular structures, sampling large design spaces, dealing with small data limits, which is a problem we encounter a lot, and uncertainty quantification. Today, what that looks like is usually we'll have some kind of domain expert in a field who will define a reasonable design space. That might be some section or segment of the periodic table with elements that they like and know work well for their design. And then they'll help us define what are sort of the criteria that will let us know we're doing a good job. And then the directed design system today is basically a neural architecture search framework. So given kind of this problem space and these constraints, you can run a large neural architecture search that will sort of find the best maybe graph neural network or transformer-based model for the set of properties you care about and help guide your design process. And so this allows kind of people with maybe more of a machine learning background to have an impact across flexible domains. And then ultimately, from the design perspective, we're usually trying to solve some multi-objective optimization, considering trade-offs with properties, and identify Pareto optimal candidates. But is that sort of the best we can do, or are there alternatives? So one thing to think about might be to move to more of this pre-training. Instead of sort of spinning up a new one-off network and doing this entire development procedure for every problem and every property we care about, can we identify and build large pre-trained models and fine-tune them to downstream design tasks and kind of take a broader picture of this. To start helping us to do this, we have been working on a very simple template called LitMatter that allows scientists to take their deep learning code and scale it up very easily without adding additional code or kind of worrying about a lot of the engineering infrastructure that can be kind of difficult and time consuming to spin up. So LitMatter will organize your model and dataset code very nicely. It allows you to keep the sort of rapid prototyping and experiment workflows that scientists love, and then investigate things like scaling your model training, again, without doing sort of a bunch of extra work. And to do this in an end-to-end pipeline without changing your workflow. To demonstrate what this looks like, I'll talk about an application to property prediction. So here we took 4 different graph neural network models and we trained them to predict quantum mechanical properties for a very standard benchmark data set, QM9 data set of small molecules. But we train these models on over 400 GPUs. So here what you're looking at is the training time it takes to train each of these models versus the number of GPUs that we trained on. So between 2 to over 400. And you can see that at least for some of the networks, we can achieve up to a 60 times speed up in the training with this multi-GPU setup. And roughly speaking, a kind of rough understanding of this might be that sort of the more complex the architecture is, that's sort of correlated with the available speed up that we can get as we do this. And so what is actually happening under the hood here? To look at this in a bit more detail, we trained not only these GNNs, but also some more maybe familiar models, including large language models like BERT and large vision models like ResNet. I just sort of want you to focus on SCHNET, circled in red here, and DimeNet, circled in orange. So these are 2 kind of commonly used GNNs for property prediction. And here we're looking at what's actually happening at the GPU level when we're looking at a single node training versus very distributed multi-node training, and what is actually being utilized on the GPU. So this is the memory and this is the streaming multiprocessor. And so maybe unsurprisingly, if you're familiar with these networks, DimeNet uses much more of the GPU. It is a heavier duty network that uses spherical Bessel functions and spherical harmonic spaces. So it has a much bigger memory footprint in general. And it's a bigger model than Schnet. But so kind of interestingly, DimeNet is really competing or outcompeting with these quite optimized sort of, again, heavy duty models like BERT and ResNet, whereas Schnet is maybe somewhere over here. To understand how these models are actually performing as we scale up, we can look at the variance in the utilization. So here we're just showing DimeNet compared to BERT and ResNet, sort of convenience, but what we're looking at here is the coefficient of variation of this utilization. So you can think about this like how busy is the GPU as we're training, and what's the variance in that busyness as we kind of increase the number of GPUs. So for something like memory utilization, this is of course going to be really sensitive to things like batch size and the model size. So we might just try to kind of fill up the GPU as much as possible. But kind of more importantly, we're looking at how does this variance increase as we give more compute to training, more raw compute resources. And as this variance increases, there are sort of bottlenecks and internode communication overhead being introduced that's raising this variance. And ultimately, that's what's going to determine how much we can scale up these architectures while still seeing improvements versus when we kind of hit a threshold.
Nathan, there's a few questions.
Yeah.
Dom, do you want to speak up?
Yeah, so I have a few questions, and one of them was actually raised by Prudencio in the chat, exactly about that plot. How many parameters are you using for the networks? Are you using a constant number of parameters even when you change the number of GPUs, or like what's the differences?
Yep, yeah, so the model is fixed as we change the number of GPUs. These are all implementations just taken directly from PyTorch geometric for kind of as much consistency as we can try to get while comparing these different models from just a sort of open source available framework. But yeah, the number of parameters are just fixed by the defaults in those examples.
Okay, and which method of parallelization on multi-GPU are you using? Because like, are you parallelizing the features, the features of the network or the batch size?
Right, yeah, so this is just the batch size. We're looking at things like model sharding and other methods for parallelization as well. But yeah, this is just the batch size.
So in the end, when you use, like you keep the batch size constant, but you split it on many different GPUs. So if your batch size was like 2000 and you use 50 GPUs, you end up with 40 on each GPU, right?
So here we're really just increasing the effective batch size and seeing like when does that so you kind of just expect naive speed up by increasing the effective batch size. You just go through the training set faster. And here we're just asking, when do the communication bottlenecks kind of hit you, and how much speed up do you get by comparing different networks?
Okay, so you have like this per GPU, you keep the same batch size. So as you increase the number of GPUs, you finish your epoch faster because you're doing all the batches simultaneously. Okay. That's it for me. Prudencio, do you have other questions or no?
No, that's all. Thank you.
Great.
Thank you.
Excellent. Yeah. So that's and that actually is great. It brings up a lot of issues that I summarize here, in that there are all kinds of different choices, of course, about how we can set up these experiments. And we might anticipate them to have different effects on what this scaling looks like. So it's hard to predict what this scaling is going to look like based on those microscopic parameters. So what we can do is kind of try to understand and actually find that this scaling with respect to compute does obey simple power law relationships. And we can try to understand, how do these different choices affect different parts of the power law? So do they affect kind of what we really care about, which is the scaling exponent? How much a network is kind of able to leverage increasing resources, or does it more affect the offset, just shifting these curves up and down, which would kind of correspond to the the sort of non-distributed training time. And so here's what that looks like for two networks, DimeNet and SCHNet. And if we fit a power law that predicts the training time, so there's this multiplicative constant alpha that again determines this offset, shifting these curves up and down. And then there's the number of GPUs n, and some scaling exponent beta, which of course depends on the model and could depend on the learning dynamics, things like the batch size and the learning rate, but not all hyperparameters. And for this alpha, there are a lot of different things that could affect this. We try to model alpha as kind of, this is an overall optimization that's shifting the curve up and down. So we actually control the clock rate of the GPU during these experiments in the amount of power that the GPU is able to draw. So we're controlling on the hardware level, sort of, the maximum amount of power that the GPU is able to draw. And we see that as we change that, we just shift these curves up and down. So that is kind of modeling all of the different optimizations that might contribute to this alpha. So actually, this is a good place, I think, to pause before I start talking about performance, if there are any other questions.
Yep, I think there is Simon and Dominic who has a question. Simon, do you want to go first?
Yeah, thank you. Yeah, Nathan, just so I understand correctly, you said, these indeed show this power law scaling, but this is not the same power law scaling we saw before, right? Like before, it was with respect to model data, sort of surprising. And here, isn't this just hardware scaling? Like, isn't this expected and completely independent of what I'm like? Do you know what I mean? Like, one is sort of a learning theory thing. This is just you stretch it across devices. Yeah.
Absolutely, yeah. So there are absolutely the scaling laws from learning theory, which I'll talk about kind of next, getting into that next. Here, this is a hardware scaling effect, which is, I guess, the sort of expectation is, of course, there will be some scaling, but that's actually maybe not as given as you would expect. And in particular, both the kind of scaling exponent and how that depends on the model, and the point where this scaling breaks down is something that we don't have a good way to predict from first principles. So in general, if we want to compare architectures, right, and say if we want to do the sort of huge scale experiments that we see with things like BERT and GPT, we need to be able to train on lots of GPUs, and that could depend very sensitively on the architecture.
Got it. Thank you.
Yeah.
Can you go to the previous slide, please?
Yeah. Mm-hmm. See if I can do that. Yeah.
Yeah. So here you mentioned that the curves follow a power law, but something I noticed is that there are actually two parts here in the power law, the first part and the second part here. And this is the case for every model where you observe this kind of double trend, and actually it fits the point much better than a single exponent. So my question in here is that instead of defining a simple constant here, shouldn't we define like this partwise power law, where the first one is we see a good scaling from increasing the GPU, and the second part we see reduced scaling. So basically in the first part here, we can see, for example, for PNA, which is the fastest method, we have a lot to gain by using 8 GPUs and less. But then it doesn't make sense to continue increasing the number of GPUs.
Yep.
Whether for other methods, this can go to 12, 13, 14 GPUs. Yeah, I think this could be a better descriptor of what's going on here. And something like, I don't know, this might be just my head seeing patterns, but maybe we can like have also this kind of curve here that defines, depending on the computation time, try to the initial computation time, try to predict how many GPUs we can, how many GPUs make it useful for the network.
Absolutely, yes. So that's like exactly how we would try to find a kind of end critical value for when this turning point is that you would see, sort of diminishing returns. And that's actually a way, the Supercomputing Center, that we can kind of dynamically control resource allocation based on the network, right? So if that sort of end critical number of GPUs is much lower, like PNA, like you see here, then it doesn't make sense to sort of allocate those additional resources. But yeah, that is exactly how we determine kind of that turning point for sort of diminishing returns.
Do you have a mathematical way of determining that critical point, or is it just like looking at the points and
yeah, nothing other than fitting power laws over different numbers of GPUs and seeing where the fit deteriorates, and seeing, this kind of, for simplicity, we're showing, and to compare the exponents, we're doing it over the full range of experiments. But yeah, we just, exactly as you did, just kind of add and iteratively add, more data points on the X side, and see where that power law starts to deviate for each one.
Okay, thank you.
Yeah. Okay, excellent. So I next will kind of jump into, this was for, so we've talked about kind of hardware and scaling of training time, but of course, what we'd really like to get to is performance and how well these networks perform, how can we accelerate convergence and scale them up with respect to not only compute, but model and data set size. And we know, or kind of we know from experiments, that's not trivial. So we need a way to kind of speed up how we're even going to go about finding good ways to scale on these methods. So I'm going to try something called training speed estimation from this recent paper. And TSE is a very simple, nice idea where you approximate the area under the training loss curve during the first, say, T epochs of training. So some limited amount of the total training you're going to do. And so this is just summing at the mini batch level or the training step level, all of the losses to try to approximate that area under the curve. And TSE is going to be a quantity that we try to use to find networks early in training that are doing well as we change model configurations. You could modify this TSE equation and say maybe there's a burn-in period where I'm going to throw away the first E epochs because maybe they're not representative of the total learning dynamics, or you could do some sort of moving weighted average where I weight more recent training steps more. But in practice, we actually find that all of these basically perform the same. And so TSE is sort of simple and cheap method for estimating the kind of converged or final performance test set or validation set performance of a network based on the training losses early in training. And so in this original paper where TSE was proposed, they showed a lot of experiments for neural architecture search in computer vision. and showed that TSC allows you to sort of rank order models very early in training and figure out, which architectures are doing the best, which lets you speed up your neural architecture search. And we were interested in, can you apply this not just for neural architecture search, but things like hyperparameter optimization. In particular, our problem is when we're trying to scale up some of these deep chemical networks, it's not the case that I can simply do my hyperparameter optimization and my model selection on a single GPU for a small model and small data set size, and then scale everything up and hope that it performs well, right? All of that changes as I scale with respect to any of these dimensions. So it really just blows up the search space as I'm trying to do this. So again, I need to be able to identify optimal configurations early in training. And so TSC, previously was used to rank order models for neural architecture search while fixing things like learning rate and batch size, sort of fixing the learning dynamics. And we want to use TSC to actually predict the model performance, not for computer vision, but for graph neural nets so different kind of architecture in a different domain, which is hyperparameter optimization. And we actually want to predict the loss if we can, not just rank order the models. So the application area here, kind of moving from just property regression to this area of neural force fields. So very briefly, the goal here is to train a network, in this case, a graph neural network, that learns the potential energy surface for a molecule. So it predicts not just properties, but it predicts energies and forces of a system and allows us to speed up things like molecular dynamics or sort of, do all kinds of interesting things with a learned model instead of training a classical force field, which can be very time consuming and requires a lot of different domain expertise than we have here, and is also much, much slower. So we want neural force fields that can accelerate simulations and are also generalizable across maybe chemical compositions and robust. So this robustness issue is quite profound, but basically as we're sort of applying these, just like you would in any other deep learning domain, you have to worry about things like distribution shift and overfitting to training data. But the problem with trying to scale up these force fields is that when we have training data in the form of some trajectory, molecules moving around, and that can come from kind of any physics-based sample or method, the higher quality, the better. But those individual frames or snapshots of what the molecule geometry looks like, when you put them together in a mini batch, that can be very noisy. And so there's this kind of interesting result from the empirical model of large batch training, that one way to maybe understand this is that when you have very noisy mini batches, like we do in this case, smaller batches and smaller steps give you better convergence. And we certainly see this with neural force fields, that in general, the smaller the batch size, the better. And that's sort of the opposite of, which is, maybe a general kind of known thing across some domains, but it's really bad in this case. And it's the opposite of the direction we want to go, right? Because we want to be training these networks faster. And certainly one way to do that is to try to move to larger batch sizes. And I will let Simon ask a question here. He's an expert in this area.
Sorry.
Yeah.
This is very interesting. I have a question. In when you train a neural force field, you have in your targets, you have one energy target, right? And if you're training on the forces, you have 3 n force targets, where n is the number of atoms. Couldn't it just be that your effective batch size is actually much, much larger? Because say you have a batch size of 10, but you have 10 atoms, then actually it's 10 times 3n plus 1, right? So is that maybe it?
Yes, I think that's totally true, right? Because the sort of information in each batch and in the loss function evaluation at each step is large, right? Because of those 3n forces. So yes, so if we want to kind of treat a larger batch, every time we add a new frame, that's now 3n more forces that we're going to evaluate. So that is, yeah, I think a fundamental issue here, which is, yeah, probably why these smaller batches work better.
Okay.
Yes.
Cool.
Yep.
Yeah, but
yeah.
we see exactly the same thing. So this is very interesting.
Yeah, absolutely. So now I'm going to talk about, maybe how do we start to try to escape this? To kind of start looking at this problem, I'll consider 3 different models for neural force fields. For convenience, these are all in this neural force field library from Rafa's group. And roughly speaking, each sort of model incorporates more physical priors than the previous one. So I'll start with Schnet, which incorporates scalar features and has rotational invariance. I'll look at Payne, which incorporates vector features. It's kind of a rung higher in the physical priors ladder. And then finally SpookyNet, which includes non-local interactions and some empirical corrections that we know from physics. And these models are sort of roughly in a family together, I would say. So it kind of makes the comparison a bit easier between them. And so in order to scale these networks, fundamentally what we need to do, if we want to train them faster and on more GPUs, one way to do that is to increase that effective batch size, but without incurring this penalty of converging much slower, getting much worse performance. So there's this sort of heuristic relating learning rate and batch size as you increase them. For these experiments, I'm going to look at what's called the revised MD17 dataset. So it's a collection of data from small molecules. There are 10 molecules, and here I'm going to take 1,000 frames from each. So kind of construct a larger sort of composite data set than if I just looked at a single molecule, like say aspirin. And for each network, I'm going to change the batch size and the learning rate. And we can see that as I increase that batch size, I get severe penalties as I decrease the learning rate. So you might expect this sort of linear learning rate schedule or scaling, where as I increase the batch size, I want to linearly increase the learning rate. And at small batch sizes, that makes maybe less of a difference. I don't incur as much of a penalty by getting the initial learning rate wrong. But as I scale up the batch size, then it becomes very important that I get the initial learning rate right. And so in general, having a higher learning rate here from the ones that we tested gives you better convergence. And certainly there is some effect scaling the learning rate with the batch size. But a cool thing here is that as we scale the data set, that allows it in kind of the chemical compositions that we're considering, that allows us to get better performance with larger batch sizes. So we can think about it like if I'm training, say, a small neural force field on a single molecule, then maybe I need to do things in small batches, and I could just do that for all the molecules I'm interested in. But if we're trying to kind of scale up the model and the data set size, I can actually maybe also scale up the resources and the training that I'm doing, and ultimately sort of more efficiently tackle this problem. This turns into kind of a multi-objective optimization where I want to maximize the batch size. In general, I want to minimize the wall time that it takes to train these networks while still minimizing the end performance or the end loss. So there's, in general, a trade-off here, but we can actually identify good candidates. And how do we do this with TSC? So like I mentioned, here's sort of a schematic for what training speed estimation looks like. It can be sort of thought of as the area under the training loss curve from just a limited amount of the training data. And again, we want to actually predict what is going to be the converged or final validation loss actually based on the training loss from the initial part of training. So what we find, I'm showing this for SNET, but it applies to Pain and SpookyNet as well, is that if we say take 10% of the total training that we're going to do, and we calculate this TSC value from that initial 10% of training, we can certainly rank order the model configurations almost perfectly. The rank correlation is very good. And these different configurations we're testing different scaling parameters. So scaling the batch size and the learning rate and trying to figure out, as we scale up the training, which configurations are going to do the best. So we can rank order those configurations early in training. And not only that, we can actually do a pretty good job of extrapolating out and predicting what that converged loss is going to be for each of these networks. So TSC is kind of a strong predictor for the converged performance using only a very small percentage of training. So it allows us to sort of zero in very early on in model selection or hyperparameter optimization or these scaling experiments and actually predict which networks are going to perform the best, which saves us a lot of time and budget as we're doing these experiments. Now I'll maybe transition in the last couple minutes here to thinking about, as we scale these networks up, how we measure different aspects of learning efficiency. So this goes back to Simon's question. I'm actually showing, I think, a wonderful plot from Simon's NetQuip paper here, where they look at the learning curve and the performance of their neural force field model, NetQuip, as you give it more data. And you can think about what these different colors are as kind of building in more physical based priors, if you're looking at just scalar versus vector or higher order tensor features. And so they show, I think, really nicely here that the increase in physical priors actually fundamentally changes the scaling behavior of this network. So the network itself, is still the same, but it becomes much more sample efficient as you build in these higher order features. And I think this is a great way to measure learning efficiency. Flops is another way. It's maybe much less preferable because flops can be difficult to measure and is generally not correlated with other things we care about, like time and energy consumption. Model size in terms of number of parameters is maybe also difficult to parse because of things like training details and model distillation and quantization. So this is maybe informative, but not as informative. And a sort of new way that I'm interested in thinking about this is actually looking at how efficient models are with respect to the energy they consume. And so I will talk about that next, very briefly, I guess, since we're getting towards the end here. Why would we care about energy efficiency? Well, there's actually some work from Mila on, of course, the environmental impact of the energy of deep learning training, which is something probably all as scientists we care about. But even there, I think there's actually great progress on reducing the carbon and environmental impact of AI. So I'm actually maybe not as worried about that as some folks are. I think a problem, though, is that the tools that you need to do deep learning very energy efficiently and with low carbon footprint are kind of unevenly distributed. It's hard to measure these things. And if you're at a very large organization with lots of great engineers, maybe you can do this very nicely, but that's maybe not widely available. I think energy is also an interesting frame to look at, especially these physics-informed models, because I think it tells us something very fundamental about learning efficiency in terms of, it couples together a lot of different aspects that flops and number of parameters and these other metrics don't get to. And lastly, it's sort of energy is this sort of universal framework that folks from all of these different communities are familiar with, maybe in different contexts, whereas again, these other metrics might be more specific to particular fields. So if we return back to kind of the beginning, looking at this different variance in utilization for different networks, what we find is that in general, and this is part of just working at a supercomputing center where we actually monitor not just our own experiments, but deep learning experiments kind of across MIT, we can see that, you know, a lot of the time the GPU is not being used. It's very underutilized, even if you're kind of doing a normal or even extensive amount of hyperparameter tuning. So this is kind of exciting, actually, because it means we're not hardware limited. In a lot of cases, there's a lot of room for improvement on the software side and the framework side. If we were hardware limited, that could be tough because hardware innovation is very hard. But there's maybe more room for improvement and opportunity for innovation on the model side than we expect if we start thinking about energy efficiency in addition to some of these other metrics like model performance or accuracies that we usually think about. One quick finding actually that came out of a lot of these experiments is that because modern scientific workflows actually don't utilize the GPU fully, the sort of top line hardware that we're using has a sort of maximum power draw of 250 watts. We don't need that. We can actually just throttle down our hardware to 200 watts, which we've started to do at MIT, and we don't really impact the speed of training or performance of training, but we can get up to 10% total energy savings for our data centers just by doing that. So that's kind of a quick system level fix here. We think about back to trying to predict performances and you actually scale models. One way to think about doing this is, so we've sort of used TSC to accelerate our scaling experiments and accelerate our hyperparameter optimization. But once we find a large network that we like and that we're going to be training a lot and might be expensive to do so, we can actually think about using TSC to predict what we expect the sort of converged performance to be, and say, maybe I'll define a threshold value and say, once I'm within, 10%, 20% of that final performance, I can early stop the model and I can use it for all kinds of experiments and get energy savings that way. Another maybe more familiar framework for stopping could be sort of early stopping with respect to patients. So normally you would define something like, if my model doesn't improve by this delta over so many training steps, I'll stop the model early. And here we can do that. We're monitoring the energy consumption during training. We can normalize that patient's value by the energy cost of training. So again, it's a small model and small data set. Your tolerance could be such that you will train it into oblivion, right? And it doesn't matter, like the energy impact is not going to matter very much. But if you have a huge model, you're training on 1 billion data points, the marginal cost for each training step is of course a lot different. And that's something that you might want to consider as you're doing training. And thinking about how this reflects actual kind of fundamental issues around model development and innovation, we can think about how energy efficient are different models, say neural force fields, actually in production or deployment. And so in this case, just like for most deep learning models, it's really inference where a lot of the costs are spent if you have a model that you actually hope to deploy and use for useful things. Here we ask the question, how much would each of these various neural force fields cost if you were to do a 1 nanosecond 100 atom molecular dynamics simulation with each of these? So that just relates to how many inference calls am I making with each of these models. And so in this case, we're looking at, say, SpookyNet and Pain, which have similar model sizes. And on this data set that I'm looking at, revised MD17, actually doesn't include a lot of the sort of parameters and physics that SpookyNet is able to capture that Pain doesn't. So their performance is very similar, but Pain saves 44% of the energy cost and the CO2 emissions for doing this kind of inference. So I think that the sort of energy aware inference and thinking about energy efficiency of models is kind of a very interesting way to compare as we build up more complex architectures, as we sort of impute more physics to them. How much are we getting out, not only in terms of, say, learning or sample efficiency, but in terms of energy efficiency. In the last minute before my conclusions, I will just put in a teaser for the fact that we are also thinking about sort of traditional neural scaling in the context of large language models for chemical generation. So we're basing this work off of GPT and asking, do chemical generative models benefit from scaling, and how so? So if you're interested in this, there's a lot of information in this chart from our initial experiments, and I'd be happy to talk to anyone about this in the future. And this probably looks a bit more familiar with the sort of traditional neural scaling work. And that's maybe the takeaway from this part is there are some surprising and interesting improvements that we see going to new regimes compared to traditional language models. Okay, so I'll skip over this stuff, go to LitMatter for all of this interesting, all of our interesting findings get built into LitMatter, so you don't have to worry about it. It just, you get it for free. Our data sets from all of these experiments are publicly available on mit.edu. And yeah, so these are kind of my final summary to wrap things up. I think that, we want to be building scientific AI that leverages key resources. Deep chemical models certainly do benefit from scale, which I think is exciting. And LitMatter is a way for you to start investigating scaling up your models very easily. And I think, issues like energy efficiency and scaling, can really help us inform new research directions for physics-informed chemical models. Here's some papers that I'll share after the talk if you want more details. And with that, thank you all for listening. Thank you in particular to my collaborators at Lincoln Lab and Connor Coley and Rafael Gomez Bombarelli. Please feel free to reach out to me via any of these methods if you'd like to chat about any of this work or anything that you're doing that I might be interested or that might benefit from this kind of scaling analysis.
Thank you so much, Nathan. It was a great talk. I hope the audience appreciate it as much as we do here. Any question? I know a lot of people left, but maybe a few more questions before we end the call.
Maybe not directly, well, related, but a bit on a tangent. You clearly have been thinking a lot about like what a foundation model could look like in this domain, in the chemistry domain. I think one thing that for me is kind of an open question still, and I think you kind of addressed it, but I'm not 100% sure, so I'm gonna ask nonetheless, is what would be a good pre-training task? Because I feel like that's a difficult open question, because in comparison to the other domains, we don't have kind of a straightforward adaptation of what they're doing there to what we're doing here.
Absolutely, yeah, that's a great question. I think would be like I could give an entire talk on just pre-training tasks and how to pick them, because I think that's a huge open problem. I think that, so for the chemical language example I gave, there it turns out to be more straightforward. We can take basically the sort of next token prediction that you would traditionally do in NLP, and it works very well for generation. For property prediction, if we're trying to train a large language model to do property prediction, it becomes much more difficult. And I would say it's kind of still unclear what pre-training tasks are useful there. I think that's a very open question. Yeah, for a question.
The masking for a generative model actually works relatively well from what you've seen so far.
It does, yes.
Huh.
Yeah.
Okay, interesting. Thank you.
Yeah, so we should have more about that soon.
Awesome.
Simon, have a question?
Yeah, really nice talk. Thank you.
Thanks.
So have you done any experiments on scaling laws of sort of property prediction, force fields with data set size or model size or compute available, sort of the classical ones?
Yes, for neural force fields in particular.
For whatever, but sort of for more the property prediction, sort of the geometric ones, I would say. Yeah.
Yeah. So for property prediction, one of the actually motivations for going into energy and force prediction was that you kind of saturate performance for, say, like QM9 quantum mechanical property, HOMO, LUMO, gaps, these sort of things, right? You kind of saturate performance so early that
Wait, so
I guess
early with respect
a finding
with respect
to model size, data set size, and
okay.
compute. So yeah, so a finding there, I guess, would be that in that regime, we currently don't have good ways to scale kind of beyond that. In neural force field, it actually looks much more promising. And we should have some interesting more details on that soon, now that we have kind of developed the framework to speed up these experiments. There's more degrees of freedom. It's more difficult to think about model size, I think, because concepts like width and depth still apply, but there are other things, of course, as you know, like nearest neighbor cutoff and other considerations. That
sorry, just I didn't know that it saturates so early for property prediction like QM9. So what's different on like neural force fields? Are you just using a larger reference data set where you can sort of span more orders of magnitude, or what's going on there?
Yep, I think it's a combination of larger data set. You can span more orders of magnitude. Certainly, the tasks are maybe harder. Yeah.
Okay. Wow. Very cool. Thank you.
Yeah.
There was a question in the chat. What are the implications of your work for something like OC20 challenge?
Yep.
OC20, sorry, OC20 challenge.
Great question. Yep. So that is one of many interesting directions that I think I already had quite a lot to cover here. OC20 is the Open Catalyst project data set, which is, I think, a great condensed phase data set for looking at all of these issues. And that's certainly something that we're very interested in. I think the implications are that catalysis, when you're looking at both small molecules and a solid state surface, becomes even more complex problem and search space. So scaling is maybe even more important.
Hi, Nathan. Can I ask you a follow-up?
For sure.
Yeah, thanks for the great talk. So we've talked a lot about chemistry, but do you also think about these geometric deep learning models in the context of structural biology, for example?
That's a great question. Yeah, so I personally have not looked at these questions in the context of structural biology. I've looked at proteins in particular as targets for identifying small molecules that bind to them. But I think that certainly with the scale and size of nucleotides and proteins and polypeptides and all these sort of systems, I think that's an exciting area, definitely a really, really exciting area to look at these issues.
Great. Yeah, thanks for the talk.
Yeah, thank you.